Hello everyone. This video is going to cover sections 10.4 and 10.5. So let's start with section 10.4. In this section we're going to solve initial value problems using Laplace transforms. Now in the previous two sections we learned how to find the Laplace transforms and then to use the table to find the inverse Laplace transforms. That's going to be the main technique we're going to use to solve these problems. Now, just to refresh your memory, the last problem we did was how to find the Laplace transform of a derivative. Okay, this is also on the formula on the table, so you can just refer to the table to use it. But this is going to be the main formula we're going to use right now, and then we're going to use the one for the second derivative and so forth. So the idea is pretty simple. You're going to apply the Laplace transform in both sides, and then you're going to simplify the Laplace transform, and then you're going to do the inverse Laplace transform, and that's going to give you the solution. Okay? Now, just to refresh your memory too, for notational purposes, remember for the notation that we have been using so far, if I say the Laplace transform of f of t is the same thing as f of s. So capital letter is going to denote the Laplace transform of the lowercase function. Okay? All right, so here in this problem, the first example, so we're going to apply the Laplace transform on both sides. Okay. All right, so if we do that, then from here, the Laplace transform of y prime using this formula is going to be s times the Laplace transform. So I'm going to use capital Y to denote the Laplace transform of y. So this is what I mean. The Laplace transform of y is just going to be capital Y. Okay. So then this will be y of s minus y0, which is the initial condition we're going to use right now. All right, so let me color code this so that you can follow this part. So this, okay, so y prime, the Laplace transform is this. Now the Laplace transform of 3y is going to be minus 3 capital Y, and then the Laplace transform of e to the 2t, if we use the formula, this is equals to 1 over s minus 2. All right, now if we plug in the initial condition, y of 0 is equals to 1, we get the following. You have s, the Laplace transform of y, minus 1 minus 3 times the Laplace transform of y equals to 1 over s minus 2. The next step is we're going to combine the Laplace transform. So if we do that, we will have y of s times s minus 3. And then we're going to move this to the other side. So this will be equals to 1 plus 1 over s minus 2. Then if we solve for y of s, then we will end up with 1 over s minus 3 plus 1 over s minus 3 times the s minus 2 they already have there. Okay? And therefore you want to solve this equation, all you have to do is apply now the inverse Laplace transform, which for this one is easy This one you had to break it into two parts using the partial fractions, which I told you that they are very, very important. So therefore, for this part, okay, you need to break it using partial fractions, and this is what I mean. So we're gonna need to find the value for A and B, so that this is the case. Okay, this is S minus 3 minus 2. We actually did this already. This is the exact same problem we did before. But just to refresh your memory, this means that A times S minus 2 plus B times S minus 3 should equals to 1. And you should check, we solved this problem already. B was negative 1 and A was equals to 1. You should check the previous video. We got these values there. Alright, so this is the how you find the values of A and B using partial fractions. So these are the partial fractions. Alright, so then from here, this is the same thing as this 1 over S minus 3 minus or plus 1 over S minus 3, because the value for A is equals to 1, and then minus 1 over S minus 2. You can combine this. This is not the case all the time, but in this case you can do it. So therefore, this is what we have so far. The Laplace transform of y is equals to this. Now, y is the solution of the differential equation. So therefore, from here, y of t, so this will be the solution, is going to be the inverse Laplace transform of 2 divided by s minus 3 minus the inverse Laplace transform of 1 over s minus 2. And if you check the table, this is equals to 2 e to the 3t minus minus just e to the 2t. So this part gives you this, and this part gives you this. By the way, notice this equation that we just solved is just a linear differential equation, which you can actually easily solve using the integrating factor. Okay, so just to refresh your memory, the integrating factor here is equals to e to the minus 3t, and then you multiply both sides by that. This one will give you y e to the minus 3t. It will be e to the minus t. You multiply by that. E to the minus t. Then you integrate both sides. You will end up with y e to the minus 3t is equals to minus e to the minus t plus some constant, or y is equals to e to the 2t plus constant e to the minus 3t. And you can see that this is identical to this. You just have to find the value of the constant. Obviously, if the question is asking you to use the Laplace transform, you have to do it this way. If I only ask you to solve this and do not specify which method, for something like this, the integrating factor is actually easier for this particular problem. It doesn't mean that this is always the case. Alright, let's do another example. Now we're gonna solve a second order differential equation, and we're gonna use the formula for the first derivative and also the formula for the second derivative, which is this, and it's given on the formula, on the table. Right, we're gonna do the same thing we did in the previous problem. We apply the Laplace transform in both sides. So for this one, we're gonna have s squared, the Laplace transform of y, minus s y of 0 minus y prime of 0. So this part gives you all of this. Then plus y prime, which you remember the formula from the previous example, is equals to a capital Y of s minus y of 0, and then minus 2 the Laplace transform of y. So this will give you this much, and obviously the Laplace transform of 0 is equals to 0. Next, apply the initial conditions right away. Remember that y of 0 is equals to 1, and y prime is equals to 4. So therefore this is equals to 1. So if we simplify, you end up with this s squared y of s minus s times 1 minus 4 plus s y of s minus 1 minus 2 y of s is equals to 0. Right, next factor the Laplace transform. So we do that, we have capital Y of s times s squared plus s minus 2. If we simplify the other ones, this, and this, we have minus s minus 5 is equals to 0. So therefore we have the Laplace transform of y is equals to s minus 5 divided by s squared plus s minus 2. This should actually be plus. Now from here, you need to use partial fractions, if possible, to factor this. So in this case, this is equals to s plus 2, s minus 1. So you do the partial fractions, you will end up with, you will have a over s plus 2 plus b over s minus 1, and this should equals to s plus 5 over s squared plus s minus 2. I already emphasized this before. This is from basic algebra, but this is very important that you refresh how to do partial fractions. Remember, from here we have the a times s minus 1 times b times s plus 2. This should equals to s plus 5. So therefore, if we select s equals to 1, the only reason why we pick 1 is because this will cancel. Then we'll have 3b is equals to 6. So that means that b is equals to 2. Then we should select negative 2 so that it cancels this one. And if we do that, we will have minus 3a is equals to 3. So that implies that a is equals to negative 1. So therefore, from here, we have the y of s is equals to minus 1 over s plus 2 plus 2 over s minus 1. Then we apply the Laplace the inverse Laplace transform to get the answer. So yt will be minus the inverse Laplace transform of 1 over s plus 2 plus 2 the inverse Laplace transform of 1 over s minus 1, which if you look to the table, this is just minus e to the minus 2t, and the other one will be 2e to the t, and that's it. That's the answer. Now, if you remember from chapter A, okay, just to refresh your memory, from chapter A, okay, so just a note. From chapter A, if you have this equation, y double prime plus y prime minus 2y is equals to 0. Remember, this is considered a homogeneous equation. So what we did there, you have the characteristic equation. Okay? And then from here, this was r plus 2, r minus 1 equals to 0. The values for r were minus 2 and 1. And then the characteristic equation was equal to c1 e to the minus 2t plus e2 e to the t, which you can see is identical to this, except that we still need to find the initial conditions. So the Laplace transform will give you the final answer. You don't have to figure out the constants. You figure out the constants when you apply the Laplace transform. And like I say in the previous problem, if I only ask you to solve this and do not specify which method to use, obviously this will be easier. But if I ask you to solve this using Laplace transforms, well, then you have to use the Laplace transform to solve the problem. All right, let's try one more example. There's actually a typo here. This should be prime, so just fix that part. You can still solve the problem if it was not prime, but this is actually easier to solve it this way. All right, just like in the last example, if you apply the Laplace transform of this one to this one, it should be s squared capital Y of s minus s y of 0 minus y prime of 0. Then for this one, it's going to be minus 2 times s capital Y of s minus y of 0. And in the other side, you're going to have 30 times the Laplace transform of e to the minus t, which if you use the table, this is equals to 1 over s plus 3. Okay, so this gives you this. This gives you this. And this obviously gives you this. Right, then apply the initial conditions. Y prime of 0 is equals to 0, so this is gone. This is equals to 1. This is equals to 1. So therefore from here we have the following. If we factor capital Y of s, you will have s squared from this one, and then minus 2s from that one, and you don't have any more capital Y. From here you will have minus s, and then minus and minus will be plus 2, and this is equals to 30 over s plus 3. Then if we solve for y of s, we will have s minus 2 plus 30 over s plus 3, everything divided by 1 over s squared minus 2s. Now notice that this is the same thing as s times s minus 2. Hence, if we distribute this with that, you multiply this times that, you'll end up with 1 over s, and you multiply this times that, well, nothing cancels, so you'll have 30 over s plus 3 times s minus 2. Right, next we need partial fractions for this part. So we're gonna have a over s plus 3 plus b over s plus c over s minus 2 is equals to 30 over the whole thing, which is s plus 3 times s minus 2. Then we're going to do the same trick we did in the last two problems. So you multiply everything by the LCD, you will end up with a times s minus 2 plus b times s plus 3 times s minus 2 plus c times s plus 3, and this has to equals to 30. Now, if s is equals to 0, you can tell right away, okay, this one is going to be gone, this will be gone, so this is what you will have left. So this will be b times 3 times negative 2, this is equals to 30. So therefore, that implies that b is equals to negative 5. You should definitely check this algebra. Then the next obvious choice, it should be s equals to 2. If we pick 2, this is gone, this is gone, and from here you will have c times 2 times 5 equals to 30. So that implies that c is equals to 3. Alright, so the last thing you should choose is negative 3. If we pick negative 3, now this one is gone, this one is gone, and you will have a times negative 3 times negative 5, and this should equals to 30, so that means that a is going to be equals to 2. Alright, so therefore, from here we have the y over s is going to be equals to 1 over s, and then plus 2 over s plus 3, and then minus 5 over s, and then plus 3 over s minus 2. Notice that you can combine these two. You don't have to, you can compute the inverse transform separate and then combine, but I'm just gonna do that for now. Okay. Then to get the final answer, then you wanna do the inverse Laplace transform. So therefore y of t will be the inverse Laplace transform of this one, and this one, which will be minus 4 for the first one, and then plus 2e to the minus 3 for the second one, and then finally plus 3e to the 2t. And this is the final answer. You should also be able to solve this using undetermined coefficients, and you should actually give it a try to see that you get the exact same answer. Now here, let me just make a side note about the partial fractions. So even here you can see that this is not hard, it just takes a while. and technically we do the cheating method. By cheating method means that we plug in values that will give you zeros at specific places. Sometimes this is not possible, like hopefully you remember that from pre-calculus. And in rare occasions, you actually have to solve a system of equations. And you may have to do that in the homework for one or two problems, but in the exams, you should always be able to do this cheating part where you can cancel things and you don't have to solve a system of linear equations. Now, from now on in this chapter, we're technically only going to do one thing, and that thing is going to be to solve differential equations using Laplace transforms. Now, what we're going to learn in the following sections is that these functions may be a little more tricky, so therefore the Laplace transform is going to be a little bit more involved, and you need to learn a few more techniques on how to solve the problem. But the idea is going to be the same. You're trying to solve a differential equation first or second order using the Laplace transforms. So the idea is going to be the same. Now, if this function is not nice, like you will see in the next examples or in the homework, then this can be pretty messy and it will take you longer to solve the problem, but the technique is going to be exactly the same. All right, so now we're going to go to section 10.5. And this is just a very specific way to find Laplace transforms. You can just always use the table and you will get at the same place. So this is just a more technical way to Laplace transform for very specific functions. This is called the first shifting theorem, and it's called the shifting theorem because you're going to multiply the function you want by e to the at, where a could be any integer. Now, to refresh your memory, to recall that the Laplace transform of any function is also denoted by f of s, which you get a new function, which now depends on s, and this is equal to the integral from 0 to infinity of e to the minus st f of t dt. And this is what we did in 10.1. The reason why this is called shifting is the following. Notice here, you can combine these two. Okay, you can combine these two. And if we do that, we will end up with e to the minus, this will be s minus a and then t. That's just factoring. And you still have f of t dt here. So pretty much it's going to be f of s minus a. So this will be shifted by 8 units, which is what you're multiplying by. And this is why this is called the shifting theorem. Now, in theory, you can already find these problems, even if we didn't call it this. So now we're just making it very, very specific. So the thing you have to be careful here is the Laplace transform of f of t is denoted f of s, and if you multiply that function by e to the at, you are shifting it by 8 units to the left. So that's what is called the first shifting theorem. For example, if you use the table, the Laplace transform of t squared is equals to 2 over s cubed. So this is technically 2 factorial, which is 2. And this is from the table. Now, if we multiply this by e to the 3t, then this will be the same thing as f of s minus 3. Now remember that this is just f of s. So for our particular example, f of s is equals to 2 over s cubed. So Therefore, f of s minus 3, it will be 2 over s minus 3 cubed. And that's it. Now, the thing that is probably more important is the following, is that if the Laplace transform of this is equals to this, remember that this implies that the inverse Laplace transform of 2 over s minus 3 q is equals to e to the 3t times t squared. This may be actually more important for what we need to do in this class. All right, let's do a couple more. So remember, from the table, the Laplace transform of sine of 6t was equals to 6 over s squared plus 6 squared. And this is what we call now f of s. So therefore, this will be f of s minus 4, which will be 6 over s minus 4 square plus 6 square, or 6 over s minus 4 square plus 36. So in a similar way, remember that the Laplace transform of cosine 3t was equals to s over s squared plus 3 squared, or s over s squared plus 9. And this is what we call now f of s. So therefore, this one should be f of s plus 4 now. And the reason why it's plus is because this is minus. So you can think as this as minus 4, which is plus 4. All right, so therefore this will be now s plus 4 over s plus 4 square plus 3 square, or s plus 4 over s plus 4 squared plus 9. And that's it. Now, to go backwards can be a little more tricky for the following reason. So note the following. Clearly, the inverse Laplace transform of s plus 4 over s plus 4 squared plus 9, clearly this should be e to the minus 4t times cosine 3t, right? However, you have to be very careful, because usually the equation is not going to look like this. You have to make it look like this, and this is what I mean. It is very possible that the equation will look like this: s plus 4, it will be s squared plus as plus 16, then plus 9. So this could be s plus 4 over s squared plus as plus 25. So this is usually how it's going to look. And you have to make it look like this. Otherwise, you won't be able to use the table. And this is where the partial fractions are going to be very useful. But this one also requires basic factoring. So here you have to realize, by looking at this, that okay, I can complete the square. So from here I can go to here, then from here I can write it like this, and then you can use the table and get the answer. Okay, so this is usually the trickiest part for these things, that if it is in this form already, you can tell right away that, well, this is equals to this. So this is pretty much how it's going to look, or sometimes even the tab has to be rearranged, like you will see in the next example. All right, so let's do an example now where we had to solve the differential equation. Now, just like we did in the previous examples that in the previous section. This will be s squared capital Y of s minus s y 0 minus y prime of 0. And this one is going to be minus capital Y of s. Now, if we use the table, the Laplace transform of this one will be 8 times 2 over s minus 1 squared plus 4. So this comes straight from the table. Okay, so this is from the Laplace table. But notice that this one is shifting sign by 1 unit to the left. So it's actually shifting to the right. I think I said the wrong thing in the previous time. So this is shifting 1 to the right. Now, if we plug in the initial conditions, we will have s squared capital Y of s minus 2s, and then plus 2 minus capital Y of s equals to 16 over s minus 1 squared plus 4. Now, if we factor the y of s, we will end up with this. Capital Y of s times s squared minus 1. Then you can actually factor the 2 from this one. And this will give you s minus 1. And this is equals to 16 over s minus 1 squared plus 4. So if we solve for y of s, we will have y of s is equals to 1 over s squared minus 1 times 2s minus 1 plus 16 over s minus 1 squared plus 4. Notice that this is s minus 1 times s plus 1. So therefore this will cancel this one. So the first one can be simplified a little bit more. So from here we will have that capital Y of s will be equals to 2 over s plus 1 plus 1 over s squared minus 1 times 16 over s minus 1 squared plus 4. Now, this part is done, okay? Because of the Laplace transform of this, the inverse is pretty easy to find. This one is the one that's going to be pretty messy. Now, remember that this is the same thing as s minus 1 times s plus 1. And this one, if you distribute, will give you s squared minus 2s plus 5. Technically, the partial fractions that you need are the following. You're going to need a over s minus 1 plus b over s plus 1, and then plus cs plus d over s squared minus 2s plus 5. Since this one cannot be factored the way it is, and you want all of this to equals to 1 over s minus 1 s plus 1 times 16 over s squared minus 2s plus 5. Okay, so this will be the partial fractions, which you will see right now is not going to be pretty. Now, if we use the exact same technique from last time, we're going to have the a times s plus 1 times s squared minus 2s plus 5 plus b times s minus 1 times s squared minus 2s plus 5, and then plus cs plus d times s minus 1, or let's just say s squared minus 1. All of this should equal to 16. All right, so we have done this multiple times. So if s is equals to -1, then from here we will have -2 times b times 1 plus 2 plus 5, and they should equals to 16. So that implies that b is -1. Or it may be easier if you put the b in front and then the -2, but it doesn't matter. So from there, b is equals to -1. If you do s equals to 1, then you're gonna have a times 2 times 1 minus 2 plus 5 equals to 16. So that means that b is equals to 2. A is equals to 2. Now, if s is equals to 0, then we're gonna have 5a plus b times -1 times 5 plus c times 0 plus d, and all of this should equals to 16. But we already know the value for a and the value for b, so therefore from here we have 10 plus 5 minus d. And how do we get minus d? Because I forgot here to write times 0 squared minus 1. Actually, let me fix them. And they should be times 0 squared minus 1. They should equals to 16. So that's how we get the minus d. And they should equals to 16. Again, this is just basic algebra. So from here, I mean, it's tedious algebra, but it's basic. Equals to -1. All right, so now at this point, we still need to figure out what's the value for c, and we cannot use the same technique that we used before, because we don't have any other values that we can plug in here that will make it equals to 0. So that's why you have to go to the system of equations. Now, if you notice, there's that if you distribute for SQ, you have A, B, and C that will give you SQ. So therefore, that means that A plus B plus C has to equal to 0. Why? Because there is no coefficient for SQ here. So therefore, the coefficient is 0. But we already know the value for A, for B, and for C. So therefore, this means that 2 minus 1 plus C is equals to 0. Or 1 plus C is 0, which means that C is equals to -1. Alright, so this is what we have so far then. The value for A was 2, so therefore we have 2, or S minus 1. The value for B, it was -1, and this is S plus 1. And then the value for C is -1, so this is -s. The value for D is also -1. And then on the bottom, we have s squared minus 2s plus 5. Remember that the bottom originally was equals to s minus 1 squared plus 4. And this is going to be very, very important, because now this part is exactly the same thing as minus. You can factor the minus 1, so it will be s minus 1, because you need that. Why? Because on the bottom is s minus 1 squared plus 4. However, notice the minus 1 times s, yeah, is minus s, but minus 1 times 1 is positive 1, and that's not what you have. What you have is negative 1. So therefore, how do we fix that? And the reason is pretty simple. You are going to subtract 2 to this. So you're going to have minus 2 over s minus 1 squared plus 4. Again, this looks like magic, but it's not, because of this. See, notice the minus 1 plus 1 minus 2 is the exact same thing as minus s minus 1. And without this, you pretty much will never get the answer. Alright, so therefore, if we go back to the beginning, don't forget that we still have this one here, which you can combine with this one. Okay, so again, you can combine this part with this. So therefore, from here, we're going to have the y of t is going to be the inverse Laplace transform of 2 over s minus 1. And if you combine this and this, it will be plus 1 over s minus 1, and then minus s minus 1 over s minus 1 squared plus 4 for this part, and then minus this one. So this will be minus 2 over s minus 1 squared plus 4. Remember this green part is now broken into these two pieces. Alright, so therefore, if we use the table, this will be 2 e to the t for the first part, and then plus e to the minus t for the second part. This should be plus, and then minus, this is where the shifting theorem comes in, e to the t cosine 2t for this one, so this goes with this one, and then finally minus 2 e to the t sine 2t, and that's the final answer. And that's it. Okay. So as you can see, the hard part of this thing was the partial fractions, and also what I mentioned at the beginning, that this is not exactly how it looks. It may look like this, and you have to make it look like this. And sometimes you have to split it into two pieces to make it work. And that's why this part is crucial to this, even though it's just some basic arithmetic. All right, so that's it for sections 10.4 and 10.5.